Good morning, and thank you for attending Blue Water's webinar, Nitrogen Compliance Stories of Success. My name is CJ Strain. I'm the Chief Technology Officer for Blue Water Technologies. For those of you whom I have not had the pleasure of meeting at local conferences, I'm a professional chemical engineer. My primary focus in wastewater is in process development, and that is my primary role with Blue Water. The format for this presentation will be pretty simple. We'll start with an introduction to the challenges and then transition to a process technology that meets some of those challenges that we highlight. We'll then wrap up with Q&A from the audience. A lot has been going on over the past few years regarding nutrient limits, especially with nitrogen in various parts of the U.S. The regulatory environment has been very dynamic. There have been parts of the U.S. where they have really focused on nitrogen as the primary nutrient of concern. I've referenced the Eastern Seaboard as an example. There are various parts of the Midwest as well that have had more of a nitrogen focus. Largely, phosphorus has been a focus through the Western U.S., but I would say across the board, that is changing slightly. You see a little bit of an equalization where they're getting both nutrients on their permits. The future of nitrogen compliance, as projected by the EPA, is going to be one of the topics at the front end of this webinar, and so we'll discuss that a little bit more. Blue Water has some very unique process solutions that are very economical. That's our primary focus, is to minimize the cost, the impact to the ratepayer. And we're going to be discussing the capabilities of those solutions throughout this webinar, as well as how those process solutions fit into the plant flow, how retrofits can be a very easy way to bring a site into compliance. And we'll go through some case histories, some recent installations that have and can provide some very useful lessons learned in a go-forward basis for design. Let's begin by examining some of the current hotspots. The EPA is requiring all states across the board to establish numeric discharge targets. Section 303 of the Clean Water Act is the primary driver here. And really what that means is each state has to come up with across-the-board numeric criteria for discharging to receiving waters. There are a handful of states that have done this, that are in actually transitioning to implementing these numeric levels. Wisconsin comes to mind. Of course, the Chesapeake Bay region has some states that have come into compliance in that regard. Florida has recently come in line as well. And there's a variety of other states that, they have specific water bodies that have nutrient criteria established, but not necessarily across the board statewide regulatory establishments. And really that's what the EPA is driving to. So again, that's multiple states are in transition there. As far as a history, some good backstories. You can look at the Chesapeake Bay region for some good stories in this regard as to the development of the regulations and how they were implemented and what kinds of solutions were really implemented. I think it's an opportunity for some good lessons learned in implementation of technology. Also, if you're looking for the current status of where an individual water body or state is, EPA does have an interactive map which can be found at the address on the screen here, and I have that map copied on the next slide. So again, this is a map showing the entire USA. It's about a year old. I've seen an updated version from March 2013, which is currently on their website, and it looks essentially the same. Not a whole lot has changed, although it is interactive, so there might be some details behind the map that have been updated. You'll note, as I mentioned before, Wisconsin and Florida and various New England states are definitely on board with or further along than some of the Midwestern and Western states. But again, all states are having to move down this pathway per the EPA's requirements. Before I proceed, I want to highlight some of Blue Water's proficiency in unit ops and give you a little bit of background on Blue Water's capability for water treatment. With challenges in nitrogen mitigation in mind, let's take a look at some specific process solutions that Blue Water provides. And beginning with really our screening, grit removal, clarification processes, we have conventional treatment options as well as a very unique process that we call our, or have branded as our EcoMat rotating belt filter. And basically that's a great replacement, a very economic replacement for chemical or for conventional primary clarification. Biological systems, conventional clarification systems, DAF systems even, in industrial applications. But really what sets us aside is our tertiary filtration techniques, our Blue Pro for phosphorus mitigation, our Blue Night for biological denitrification, and we do a lot of water reuse applications as well. We're a US-based manufacturer. All of our manufacturing is done here in the US, and we use US components as much as possible. Our primary manufacturing facilities are in the state of Idaho. We have steel and FRP shops, UL panel. We have a UL listed panel shop as well. That gives us a lot of flexibility when we're delivering a solution to a client because we can customize the control system and make it very easy to integrate into a plant SCADA system as well. In addition to that, we do make mobile or contract treatment systems that might be online for a temporary turn. For example, we've had some projects come up where dewatering is required during construction phases. You have groundwater that needs to be treated, and sometimes even a couple of million gallons per day on a 6-month contract term. So we're very flexible, very capable of meeting some of those contract treatment requirements as well, and so that's why I've shared some pictures of our mobile systems in the upper right there. Well, let's jump right into nitrogen. And to understand nitrogen removal, it's important to examine the sources of nitrogen in discharge waters. Now, nitrogen in our wastewater streams mostly come largely from our biological systems, from human waste. Primarily in the forms of urea or organic nitrogen as sources for nitrogen in the water. So there's DNA, RNA, urea. Here's an equation for the breakdown of urea and formation of ammonia in the water, and that process is called ammonification. Further biological activity throughout the wastewater treatment process, primarily nitrification, can convert ammonia to a nitrate form. So that nitrogen is oxidized to a nitrite or a nitrate form, and typically the driving bacteria behind that are Nitrosomonas and Nitrobacter. Now this process consumes alkalinity. It typically would lower pH if it's not a well-buffered system. And really the focus within the last decade, certainly the last 15 years or so, has been to not fully drive this equation to completion as an independent process, but to really pair it with a denitrification process and kind of shortcut this cycle and go from ammonia to a nitrite to a nitrogen gas kind of process. But again, that typically would happen within the secondary system. As a denitrification system in a tertiary application, you are converting those nitrates, nitrites into nitrogen gas. And this is a process that requires facultative heterotrophs. It's an anoxic process, so it is an oxygen-deprived environment in which these heterotrophs are growing, reproducing, and denitrifying. Also, it requires a carbon source. Conventionally, what's used is a methanol for a carbon source. Very high in BOD, very easy for biology to break down and integrate into their cellular respiration cycles. A trend certainly that's been around, I would say at least the last 10 years, has been to move away from methanol as a carbon source because of its safety hazards and go with alternative carbon sources, which I'll detail in case histories as we jump forward here. But another aspect of this entire process is you get a production of alkalinity, so it often balances out the consumption of alkalinity that you would get in the nitrification process. So there's kind of a broad overview of nitrogen cycles in wastewater. Now let's focus on the different techniques available to remove nitrogen from the water. Different technologies have been used over the years. Ion exchange is one of the top ones for small scale systems. It typically kind of shied away from because it is typically associated with a higher cost, higher operations, maintenance, life cycle costs. But it is a capable system for doing nitrogen scrubbing from waste streams, and you'll find it on some systems that may not have the space or might be more mobile than some more conventional and more economic processes. Biological nutrient removal, I'm sure everybody's familiar with the desire to go that route. It takes advantage of resident carbon within the water, typical of wastewater and waste streams. And it would use an expanded secondary, so more reaction time, more zones, anoxic and aerobic zones to nitrify, denitrify. Now the problem with that is a lot of plants don't have the space. Typically when these reactors get that large, there's a lot of capital and operations and maintenance costs involved as well. So it could be very useful in applications where you have to meet a 10 milligram per liter nitrogen or nitrate limit, but once you get below that, it often makes sense to have a tertiary or enhanced nutrient removal system at the back end of the plant to denitrify the less than 5 or less than 1. So just a couple of options there, or broad categories for denitrification technology. For further reading, and there's some really good stories, some really good models in these papers that I've referenced here. Paul Sutton et al. Continuous backwash filters, which is what we're going to primarily be talking about today for the Blue Knight process, using our system that Blue Water has provided to the industry and has a lot of really good success stories with. There's also another paper by Thomas Wilson, a critical review of common nutrient removal options, and that one's really good because it's more of a survey. So a couple of references that I would encourage you all to look at. Now let's jump right into the topic that I really want to focus on, and that's the Blue Knight process for biological denitrification. We're going to be talking about the operations, the design, and some case history in that regard. Hopefully those will be good tools for any engineers that are thinking, or any cities that are thinking about having to upgrade to a denitrification process. I want to start by defining the vessel in which the denitrification takes place. This is really the platform and the tool that Blue Water uses not only for denitrification but for our phosphorus removal technologies as well, and for water reuse. It's a very capable, very flexible platform. The CentraFlow filters, they're continuous backwash gravity sand filters. So what that means is there aren't any mechanical components within the filter itself. The bed turnover happens by gravity and by an airlift. So the operations and maintenance costs are extremely minimized with this system. I would say that the shortest life component within the system is the airlift, and that'll last at least 10 years. So again, a very low life cycle cost for this this technology, this platform. The continuous backwash nature is very critical as well, because with a continuous backwash filter, you have a very consistent effluent water quality. Your process, it hums. Compare that or contrast that to static bed filters or cloth disc or even membrane filters where you have backwash cycles. And a filter cell or subsystem would be taken offline and backwashed, and as it's put back online, there would be a certain amount of carryover into the effluent. That becomes a critical downfall to those systems when the effluent quality permits are exceptionally stringent and strict. So the continuous nature of these filters is very critical. And they do produce a very high reuse effluent quality. These systems, they can be installed above ground in round tanks. We have many installations, in fact, some of the largest installations in the world even utilize this configuration. I've seen basically, they look like fields of filters operating in Europe and in Saudi Arabia, where there's 100 or so of these vessels. on concrete platforms. That is, one optional configuration for these systems. Another one is more common for larger plants, and that's to install in concrete, where you could have multiple filter airlifts in a concrete module. It makes the capital costs, reduces them slightly while still being able to maintain your redundancy requirements. So just a couple of looks at how these systems are installed. I mentioned that the central flow filters with the Blue Knight process are very easy, very simple to retrofit. I would say that 90 to 99% of our systems today have been installed as retrofits. Typically you have a lagoon system, activated sludge system, well, basically any kind of system that's been installed and operating for a few years, and their permit level changes, or their permit, they get a nitrogen level on their permit. So they have to consider additional treatment. So again, this process, very simple to retrofit. It's a system that once you plug it in at the end of the treatment train, the backwash, which would have the mature biomass that's been wasted from the filter, could very easily be taken back around to the front end of the secondary process. And that way the sludge management could utilize existing infrastructure. So just a couple of design notes again in that regard. As far as the process itself, Blue Knight for denitrification, again, this is a nitrogen removal technology, and we have installations across the U.S. and across the world, really. Nitrogen or nitrates can be lowered to levels that are nearing the detection limit. We have a lot of permit levels that are less than 0.3. We even have one as stringent as a less than 0.1 as some extremes. We have others that aren't quite as stringent, that are maybe a less than 10 or a less than 5 milligrams per liter of nitrate as well. So just a couple of broad ranges that we would typically target. Adding filters, just as a side note, is often a lot more cost effective, as we alluded to earlier, than reconfiguring the secondary system for BNR to extremely low levels. So just keep that in mind as we go through some of these case histories. I want to take just a minute to talk more specifically about the process as on a unit operations platform here. So this is the Blue Knight process diagram. It's a cross-section of a central flow filter integrated with a controller PLC for control of the denitrification process. Essentially what you have is secondary effluent or process water coming in. It's mixed with a carbon source. Again, the DeNite process requires a carbon source for cellular respiration and conversion of that nitrogen. So that carbon source is mixed. The process water then enters through a central assembly and is distributed to a media bed through radial distribution arms. The water would then flow upwards through the media and over a fixed effluent weir at the top. A portion of the clean water is actually used for backwash. You can think of the wash box here as a cylinder that's open top and bottom, and a portion of that clean effluent will flow up through that cylindrical geometry. And it'll carry away the biomass waste and any filtered contaminants. If this is a Blue Pro system for phosphorus removal as well, all of your phosphorus contamination will also be carried out that stream as well. So that's basically how the backwash cycle works. It cleans the media very well. Cleaned media would then fall back to the top of the filter bed. I consider this a reaction zone here. So as the media falls through the bed at roughly a quarter to a half inch a minute, the biomass, the attached growth, it's becoming more mature. It's growing. It's converting those nitrates to nitrogen gas, and again, like I said, it's picking up and converting within this reaction zone here. Once it crosses, or once it passes the radial distribution arms, it's no longer actively treating water, but it's more in a compression zone where this you get a lot of sloughing of that biomass. The mature biomass sloughs off of the media. You get some scrubbing action in here, and the airlift here, which transports the media up to the wash box, further enhances that scrubbing. So by the time the media reaches the wash box, your biomass has sloughed off, and the media is free to return to the bed for another cycle. So that's basically how the Blue Pro process works. It requires a PLC, some sensors, and some integral and advanced controllers to really maintain some of the higher levels of treatment that we've discussed and will be discussing further on in this case history. A couple of design notes that I want to make. One of them pertains to the media that we use within these systems. We like a very spherical geometry. We don't want subangular sand that can interlock or bridge. We want a very spherical geometry. This is lessons learned from other more conventional uses for these filters in the industry. A lot of folks have used these filters for coagulation filtration. They've tried to minimize the interstitial spaces between the media to lock in all the solids. But really what that leads to is bed failure, that kind of thing. So again, we like rounded media. It gives better process reliability. It's certainly easier to sustain because you get more free flow through the bed. And it also gives a very good surface area for attached biogrowth. So a couple of reasons why to go with a spherical geometry in your media. Some of the design parameters that we integrate into our process control scheme really rely on what's happening here on the chemical level and biologically within the vessel. So the chemical reactions that are taking place, they basically, or the biological uptake actually converts the carbon source and the available nitrogen or nitrates in the water to nitrogen gas. You get evolution of CO2 in the process as well. It gives you some of your buffering capacity, your alkalinity. And so that's basically the process going on. And again, this is a chemical formula or equation using methanol, but we've used a lot of alternative carbon sources, including glycerin products, acetates, acetic acid. There's a variety of alternative carbon sources that are available that are non-explosive. They have slightly better, in my opinion, resilience to temperature changes because they typically use a broader array of heterotrophic bacteria, whereas when you're using methanol, you're locking yourself in really to methanogens, which, again, it's a very efficient process, but there are some benefits, both safety and process consideration with going to non-conventional carbon sources. You have a couple of numbers thrown out there for specific total consumption of nitrates and some biomass production, both important design parameters when you are looking at plant design. Typically, some of the additional notes that we like to throw out there as considerations, DO is going to be critical because, again, this is an anoxic process. It'll consume all the DO before it actually starts converting those nitrates to nitrogen gas. Temperature is important. The type of carbon source will sometimes greatly affect, I shouldn't say greatly, I think that's an overemphasis, but it will have an effect on the dynamics of the biological growth in the process overall. And really it's critical that an effective process control, an effective PLC and control scheme really integrate the proper parameters to really compensate for all of these design considerations. Blue Water does have a patent pending process control system for our Blue Knight process, so we've been doing this for a long time. We have a very capable system, as you'll see, again, in some of the stories that we have to share. And one last note, phosphorus removal can be simultaneous. That's an additional process add-on, but again, it uses the same vessel, the same infrastructure. So it's actually a very effective, very cost-effective way of mitigating a phosphorus concern as well. And I'll have a couple of notes in that regard going forward. I want to talk about case history now. This first one is Bellefonte, Pennsylvania. It's an installation that we've had running since 2009 now. It's a 6 MGD flow, and it has a really interesting story because originally it was piloted and designed because of a nitrate requirement, but they knew that they would eventually also have to worry about total phosphorus. And as I mentioned before, this is a flexible platform where you could do both within the same treatment stage. One's a biological process for denitrification, and the other is a chemical adsorptive process, which we call BluePro, for adsorption of phosphorus. Again, another high efficiency process. So they originally installed for denitrification, and then very simple addition for mitigation of total phosphorus, just another control system with chemical using the same equipment platform to mitigate their phosphorus. And again, it's been running very successfully since 2009. And this is one of those plants that uses a glycerin-based carbon source. Another case history that I want to share, and this one is an industrial case. It's not directly relevant to municipal sewage, etc., but it does tell a good story of how resilient and how flexible this platform is to high levels of nitrogen. It shows off some of the capabilities of this platform. So it's a smaller design flow, but the influent nitrates are anywhere from 150 to 200 milligrams per liter, and they have an effluent target of less than 10 milligrams per liter nitrates. I will say that they usually average less than 1 here. They've gone through 2 other expansions, so the site and the customer are very happy with the process. It's been operating since 2011. This case history here actually has a very good, this was a very well modeled case as well. The engineer did a really good job of defining the objectives, the parameters at the front end of the project, and it was very well modeled. Some great design information, and this one actually contrasted the growth dynamics and the operation between a methanol-based system and a glycerin-based system. And this project was in Katy, Texas, and warmer weather. It basically showed that methanol and glycerin can be used to achieve the same end result equivalently. So that was a very good process for that. And this was another project that also looked at total phosphorus removal as well. Again, this was done in a single stage. It was BluePro for total phosphorus removal, and BlueNite for removal of total nitrates. 2 primary process chemicals. They were the only additions on an operations and maintenance ongoing basis. Ferric sulfate for the adsorption of total phosphorus, and then a carbon source was added for the biological denitrification. Indian Head, Maryland, this one falls within that Chesapeake Bay region that I alluded to earlier when we were talking about the history and the future direction of nitrogen mitigation around the U.S. and especially, again, the Northeast, the eastern seaboard there. Engineer was Brown Caldwell. A smaller plant, six filters here, 2.6 MGD design flow. The deliverable here was very tight, though, for the total nitrogen. Or total nitrates, I should say, less than 0.1. So again, this is one of the strictest, most stringent requirements that I've seen out there, and it does require a very effective controller because again, we're adding a carbon source. So what you're doing is you're balancing the effluent BOD and the permit limit within your controller. So it has to be a very well tuned controller, and again, that's a patented controller that we use with our BlueNite system to maintain a very low BOD effluent as well as hit that very low total nitrate target. Their total phosphorus target, not extremely low, about a 0.3 here, and that's actually very simple to meet with our BluePro system. Installation has been operable since 2010. This last case history that I'm going to talk about, it doesn't have a nitrate permit yet, but it's very illustrative of a BluePro system that can be modified to meet nitrogen requirements in the future. This is in Marlborough, Massachusetts. Fairly large system. They have a peak design flow of nearly 12 MGD. Their deliverable is less than 0.07 milligrams per liter total phosphorus. It's been running since 2011 with very good performance, as noted here in the lower right-hand corner. But again, this is an example of a plant, a very forward-thinking user who knew that they're getting a stringent, a very stringent phosphorus requirement. Again, this is a single-stage system. and they were having to meet a 0.07 total phosphorus. And they knew that, in the future they might get a nitrogen requirement. So this platform, going with this system for phosphorus removal, really opened them up for future as well. So it's a smart investment. It took the most flexible solution currently, a very cost-effective solution in its own right, and it's protecting the ratepayers in years to come. The last case history that I'm going to share, this is another installation in Virginia. It's an AECOM project, 16 filters in this particular installation, nearly a 4 MGD design flow. The deliverable here was written as a total nitrogen requirement. So again, this process, biological denitrification, it's only removing the nitrate component of that, but sufficient to meet their 3.5 total Len permit. And then they also have a phosphorus component as well. So I shared all of these case histories that have a phosphorus component because, again, I think that eventually they'll go hand in hand. A lot of sites will have to consider both. And so I share this as a very flexible platform for achieving that goal. I mentioned some design considerations earlier, and I just want to reiterate those before we close here. Temperature effects are not an insignificant consideration when designing a denitrification system, a Blue Knight system. Because, again, as we all know from refrigeration, biology reproduces very slowly at lower temperatures and very quickly, very rapidly at higher temperatures. So you see two curves, and you can think of these as maybe a summer-winter curve here, with the summer curve being or reflecting higher efficiencies than the lower temperature curve for given detention times. And so again, this is a curve out of Metcalfe and Eddy. You'll see it all over the place, but again, it illustrates those temperature effects. Once you get below 10 C, you reproduce so slowly that your reactor volume, your detention time, goes up exponentially. So just some things to keep in mind. It's not very often that I see winter permit levels, at least as long as the the site has been permitted in a realistic manner. The winter concerns aren't as stringent as the summer concerns for discharge. So typically, if we can design around the summer curves, it's a much more cost-effective system. If you do have to design around cold weather, your reactor volumes can get pretty big. Another note on temperature effects relates to startups. Startup and commissioning new systems. One thing that I like to point out here is you're balancing two things. You don't have any biological population when you're first starting up, so you have to, or you have to build up that biomass to get the critical mass for denitrification. In this particular application where I got this data set from, it took roughly 4 weeks. So the influent nitrates, they're bouncing all over the place from 10 to 20 plus milligrams per liter on this chart. And it takes about 4 weeks to really grow up that mature biomass if you're starting from scratch, where you're not seeding the population. And this was a colder temperature application with a water temperature around 12 C. If you can seed the bed, you can cut this probably about 2/3 of this time off, and you can seed it with lyophilized, freeze-dried biomass, or you can simply use WAS from the site. We typically prefer that because then you're using resident bacteria to that region in that plant. So you can basically dose that to the system as you would a chemical, keeping in mind the high solids that would be typical of a WAS stream. The other thing that really shortens up this time is temperature. If you're starting not at 12, but at say 18 plus degrees C and seeding the bed, you can be started up in as little as a couple of days. So just a couple of considerations for startup commissioning if you have a contract project coming up, or if you're piloting, those considerations really come into play. Now, Blue Water can demonstrate or offer systems for a contract, like I had noted. We use them a lot for treatability projects or for full-scale design on a pilot scale. Economic analyses are also pretty critical at the front end of a project, and these pilots can be very helpful for modeling a process in that fashion. This is in the upper left, a system that we would supply for that. It's a 50-foot flatbed trailer. Everything that you need is on board here. It's got the controls, all the instrumentation in the container, 20-foot container. And then it's got the filter vessels with the media that would be required for operation. And this particular system has a peak flow of roughly 70 gallons a minute. We have some other systems pictured here that we use for piloting equipment or for contract treatment in other kinds of applications as well. So again, just highlighting some of our capabilities. So we've covered a lot of ground today. We've talked about the regulatory environment, the future of nitrogen discharge. That could be, anybody's guess exactly where we're going to end up in across the industry. But I do see a lot of hotspots around the states that are requiring nitrogen levels that are very strict. And some of those locations also require phosphorus levels that are getting more and more strict as well. So that's the broad future. Again, like I said, anybody's guess where we end up, but I see that coming along as we live and breathe today. We've given a pretty broad overview of Blue Water Solutions and the Blue Knight process and the various aspects of that. So I hope this has been a very informative webinar, and I would like to open it now for questions, although I do have one more plug before I do that. This is the model EM1. This is the EcoMat rotating belt filter, and it's Blue Water's new product launch for 2013. We're going to have one of these models at our booth, booth number 1660 at WEFTEC. This is a 75 gallon per minute replacement for screening and primary clarification. So again, the target market for this particular model is small package plants, membranes or RBCs that have fouling issues with rags, hair, or plastics. So that's really our target market there. We'll have a unit in our booth, and we'll have that beer as well. So stop by and say hi to us. Check out the EcoMat, the baby of that product line. We do have large units that in an individual unit will treat up to 3.7 or 3.4 MGD in a single unit. So stop by our booth for that. So now we'll open it up for questions. If you have a question, please type it into the pane, the GoToMeeting pane on your screen, and we'll answer those as they come up. Any questions beyond that, you can email to me directly at cstrain@blueh2o or bluewatertechnologies.com, and our website is on the screen as well. There's some additional resources that we post on our website, and we'll have a copy of this video up there as well once we've completed this webinar. One of the questions that just came in: how does the media how often does the media have to be removed for component replacement and repair? And the short answer to that is you don't have to remove the media for most standard maintenance and repair. Again, we've said this, we've shared that this system has a very long life cycle, 20 years plus for most components. The airlift itself, which is a replacement part with maybe a 10-year life, it takes about 5 minutes to swap those out. You don't need to remove the media for that. If you're at the end of life for one of these systems, you're at the 30-year mark, etc., you're past the design cycle or design life for the system, and you might have an internal pipe failure. I showed you that central assembly. That would be an example where you would have to remove the media as well for that maintenance. But again, that's the end of life for the equipment. What is the sand media replacement frequency? Another good question. The media itself does not have to be replaced very often. In fact, we've got systems that have been running with the same media for over 20 years. So again, it's not considered it's not what we would consider a consumable. It's once you charge the filter vessel with media, it can stay in there. And over the years, early in the conception of continuous backwash filters, and there's a lot of different designs and vendors out there. Some of the wash boxes were poorly designed where there was a lot of media carryover into the reject waste stream. I would say in the last 10 to 15 years, most manufacturers have mitigated that. Certainly with our platform, the Centriflow brand, and the Blue Knight process, we have little to no carryover at all. So we don't lose any media. The media that you charge the vessel with has a very long life. Another question, are there any installations in Canada, BC in particular? And my answer to that is yes, we have installations throughout Canada for the CentraFlow filters, typically in reuse or to polish solids at the end of a plant prior to discharge to a receiving body. So we do have a lot of installations. The number of nitrate installations per se are fairly low. Canada has been looking at nitrogen removal. The various territories have been looking at nitrogen removal. But again, I think we're at the front end of that process of converting over and making sure that all sites have nitrate solutions for protecting the environment. So I'm not sure if we have any specific installations that are denitrification in BC, but we do have installations. And again, any of those installations could be very easily retrofit with the controller and the chemical system for the Blue Knight process. Next question, how low of phosphorus will you guarantee the effluent in a single stage when doing denitrification? So a lot of times we'll say that below 0.1 is an easy application for phosphorus mitigation. And certainly when you're doing denitrification within the same stage, it adds another level of complexity. But as we saw in one of the case histories, let me see if I can get back to it quickly. Here we go. This one is in Texas again, where they were doing a significant amount of phosphorus removal within the same stages of the denitrification, approaching that 0.1 mark. So that's again why I say, we could easily hit that 0.1 mark and still fully denitrify. Once you start getting below that 0.1, you do start starving the biology of a critical nutrient that is required for cellular respiration for phosphorus. So, in that single stage, 0.1 is an easy mark. When you start looking below that, like Marlboro had a 0.07, we have installations that are achieving a 0.05 phosphorus discharge. Once you start getting in there, you definitely have to make sure that your denitrification is happening in that first stage where it can still access that phosphorus. We do have some two-stage systems that, again, they're designed to hit that 0.05 milligram per liter phosphorus mark, and you can't denitrify in the second stage. There's just not enough phosphorus there. So I hope that answers that question. Next question, what is your experience with simultaneous NMP? Well, again, all of the case histories that I shared, I purposely chose case histories that had both simultaneous nitrogen and phosphorus removal. We've got a lot of systems out there that are very successful, and I would say we're the best in the business at doing that with this kind of platform. Next question, what do you mean by effective control? Well, as I mentioned, Blue Water has a patented control system. There's a lot of parameters that you have to account for in denitrification. As I mentioned, dissolved oxygen, temperature effects, the loading rates, the amount of nitrogen you're removing, detention times, etc. So there's a variety of factors, and your control system has to effectively balance that, especially when you're shooting for the low levels, the 0.1s for total nitrates out of the back end of the system. Those are very tight controls. When you're adding a carbon source to achieve that, you can just add tons of carbon source, but typically you have a BOD consideration as well. So again, a finely tuned controller is critical, and a flexible controller is critical to balance that and keep the water quality within site discharge requirements. Next question, what amount of incidental removal of BOD and TSS can be achieved within the D-Night filters? So again, TSS removal is going to be very similar to a reuse application. These systems we have installed for water reuse, and your effluent TSS is going to be less than 5 milligrams per liter, almost always across the board. As far as BOD polishing, again, we're adding BOD to the process to feed the biology for denitrification. So again, you're going to rely on your controller for really minimizing that BOD and balancing the BOD effluent level with your nitrate level. So again, if you have a stringent nitrate level, you might be having to add BOD, and you're relying on your controller to keep that BOD level within the site discharge requirements. So I hope that answers your question as well. Last question, I was unable to attend the first half of the webinar. When will it be offered again? Again, since we're running out of time, this is the last question that I can take. This video, this webinar will be available on Blue Water's website and on our YouTube channel as well. So if you didn't make the entire webinar, or if you want to refer a colleague to this webinar, it will be available on our website. Again, this is the last question that we have time for. If there are further questions, you can email the address on the screen, or you can go to bluewater-technologies.com. We do have a contacts link on the website where you can get in touch with a local rep or a local regional sales manager. So I want to thank each and every one of you for joining us today on this webinar for biological denitrification, and where I got to share some of our case history, some of our good stories with the Blue Knight process. I look forward to working with you in the future. If you have any specific applications or projects coming up, please feel free to contact us. We do have a lot of good experience to share in this regard, and we are able partners to help you succeed in your various projects. So again, thank you all for joining us today. I look forward to seeing you at future shows and conferences.